Welcome back. In the last few videos, we've been talking about how to go from matrices to linear transformations. And what we have now is we now have a correspondence between linear transformation on Euclidean spaces and matrices. It turns out that this correspondence preserves much of the structure. In fact, the composition of linear transformation on Euclidean spaces corresponds to matrix multiplication. In fact, I think that's where matrix multiplication comes from. It's coming from composition of linear transformation, and invertibility of linear transformation corresponds to invertibility in matrices. All right, so the correspondence from A to T of A preserves a lot of the structure. Products here corresponds to composition here. Inverse on one side corresponds to inverse on the other side. So let's put that into proposition 2.3.2. For linear transformations, TA and TB, if I want to compose them, that'd be the same thing as taking T of B times A. All right. For any linear transformation, the kernel of T of A, that's going to be the null space. And the image of T of A, that's going to be the column space. That's why we care about these spaces. When you start talking about linear transformation, these are going to be important. All right, so a linear transformation T of A is an isomorphism if and only if the corresponding matrix is invertible. All right, so this is nice because it's easy to determine if a matrix is invertible. We have the determinants, we have the reduction, we have tons of tricks. And so we're going to use our knowledge of matrices to prove that linear transformation or isomorphism. That's a bit harder. We have to talk about kernel and stuff like that. And if T of A is an isomorphism, then its inverse, T of A inverse, corresponds to, well, the matrix A inverse. All right, so that means T of A inverse is T. I'm saying the same thing twice, but the inverse once it's on the transformation and once it's on the matrix. All right, so let's prove some of those. I'll leave some of those for you to do in the worksheets. All right, so let V be any vector in Rm. I want to prove that these two maps are the same. So let's just spell out what they are on V. If they are the same thing on a random vector, then they'll be the same thing. All right, so the composition means that you apply TA first, and then TB. Applying TA just means multiplying by A, and applying TB just means multiplying by B. So this is what I have. Multiplication in matrices is associative, so I can change the parenthesizing of this. I'm going to get BA times V, and well, multiplying by BA, that's what TBA does. All right, so this map and this map agree on a random element, and so they're equal as functions. All right, so let's prove property 2. So for any linear transformation, kernel of TA is the null space of A. So let's prove that. I'm going to take an element in the kernel, and I'm going to show that it is in the null space. All right, so I want TA of V, that's AV. All right, so V is in the kernel if and only if TA of V is 0. Well, TA is AV, so if and only if AV is 0, and that was exactly what the null space was. All right, so the kernel and the null space have the same element, which means that they're the same set. All right, final thing I'll prove for you guys is that the image of T of A is the column space of A. So I'm going to take C1 through Cn to be the columns of A, and I'm going to figure out what the image of an element like this is. All right, so if I apply TA, that's multiplying A while I have the columns of A times the vector. And again, when we multiply a vector by a matrix, the first component of that vector will always multiply the entry of C1. And so what you'll end up doing is taking A1, C1, and then A2, that one will multiply C2, so you end up with A2, C2, and so on. All right, so that's the function. So if I look at the image of TA, it's going to be everything I can hit, so anything like this. It's going to be A1, C1 plus A2, C2 plus AN, CN. All right, and I can take any of these, and so for all R, that's exactly the definition of the span of the vectors C1, C2, Cn, span of the columns. That's exactly the column space. That's the definition of the column space. All right, and like I said, 3 and 4 will be on a worksheet or an assignment.